When you sent in those excerpts from The Science of Interstellar, I gotta say, I was hooked. Kip Thorne diving into the science behind the film, that's what deep dives are made of.
You're spot on. It's a goldmine. And Thorne wasn't content with just advising on the film. He was right there, shaping the science, making sure those stunning visuals of Gargantua, the black hole, the wormhole, weren't just pretty pictures, but based on real physics.
It's one thing to be wowed by the visuals, but knowing it's rooted in actual science takes it to a whole other level. So for those of us who might have missed the finer points amidst, well, the sheer awe of it all, where does Thorne take us beyond the screen?
One of the coolest things is how he goes beyond what we see. Like he lays out a whole scenario for how Professor Brand could have even discovered the wormhole in the first place.
Talk about bonus content. All right, so before we get too deep into black holes, maybe a little groundwork, how does Thorne set the stage?
He starts us off on this cosmic tour, reminding us that our universe is this mind-blowingly vast expanse of stars and galaxies and, of course, planets. And he even gives a shout-out to Andromeda, our closest galactic neighbor. Fun fact, it has a black hole at its center, 100 million times heavier than our sun.
Okay, well, let that number sink in for a second. 100 million. That definitely puts things into perspective.
It really does. And then he walks us through the life cycle of stars, like our own sun. Some just kind of fade out, but others, they go out with a bang, collapsing under their own gravity to form these incredibly dense objects. White dwarfs, neutron stars, and of course, black holes.
Okay, I'm hooked. So how does he explain the differences between these cosmic heavyweights?
He uses this really cool comparison of their sizes.
Sure.
Picture a white dwarf. It's about the size of Earth, but a million times denser. Then picture a neutron star, just 20 kilometers across, but packed with even more mass. And then there's the black hole, with a circumference of a mere 22 kilometers for one with the mass of our sun.
It's mind-boggling to think about that much mass packed into something so tiny.
All right, it's like, how does that even work? And that's where Einstein's theory of relativity comes in. Thorne explains it beautifully using this analogy of an ant on a trampoline.
Okay, I'm intrigued.
So imagine a bowling ball on a trampoline. It creates a dip, right? That's what massive objects do to space-time.
Okay, I'm visualizing this. So the heavier the object, the deeper the dip in space-time.
Exactly. And that dip is what causes gravity. Objects are basically following the curves of space-time created by these massive objects and those mind-bending visuals in Interstellar. The way light bends around Gargantua. Thorne makes it clear that's not just artistic license, it's based on real equations, straight from Einstein's theory.
So we've got this warped space-time, but what is a black hole, according to Thorne? Is it just this giant vacuum cleaner in space?
That's a common misconception, and Thorne addresses it head-on. Black holes aren't made of matter like you and me. They're made of this warped space and time. And at their heart lies something even more bizarre, the singularity. It's where things get really weird, let's just say that.
Okay, so not just a giant sucking void. There's more to it. So tell me about this singularity. It sounds kind of ominous.
Well, Thorne gets into this concept of the event horizon. Think of it like the point of no return. Once you cross it, there's no coming back. And at the very center of that event horizon, that's where you find the singularity. We're talking about a point of essentially infinite density. Our current understanding of physics just kind of breaks down.
Okay, now I'm really intrigued. And Gargantua, the black hole in the film, what makes it so special?
Ah, Gargantua. It's a whopper, even for black holes. Thorne explains that black holes, they come in different flavors, spinning and non-spinning. And that spin, it affects their appearance, how they interact with their surroundings. Gargantua, to create those crazy time-warping effects, well, it has to be spinning at almost the maximum speed physically possible.
You're talking about that whole 1 hour on Miller's planet equals 7 years on Earth thing, right? Time dilation. It's like something out of a dream, but this is actual science.
Precisely. Thorne calculated that to get that level of time dilation, Gargantua's skin has to be pushing the very limits allowed by the laws of physics. He even breaks down this concept of the shell of fire, this region around a rapidly spinning black hole that actually plays a role in creating its shadow, something telescopes might actually glimpse in the future.
So we might actually get to see a black hole's shadow. That's incredible.
Speaking of wild rides, Thorne also talks about gravitational slingshots, right? How spacecraft can use the gravity of planets to get a speed boost.
Yes. He uses the example of NASA's Cassini mission, which used the gravity of planets to slingshot itself all the way to Saturn. But then he takes it a step further, explaining how Gargantua's immense gravity could, in theory, create slingshots of, well, mind-blowing power.
Okay, now I'm just picturing spaceships whipping around black holes like they're going down a water slide. But wouldn't that be a one-way trip? I mean, if nothing can escape a black hole.
Well, that's where things get really interesting. Because Thorne also dives into wormholes, these theoretical tunnels that could connect distant points in space-time. Wormholes. Now we're talking shortcuts through space and time. Did Thorne think those were possible?
Thorne doesn't shy away from the challenges, that's for sure. He explains that to keep a wormhole open and traversable, you'd need something called exotic matter, which sounds like something straight out of Star Trek, right?
Exotic matter. What is that? Some kind of cosmic fuel?
Think of it as matter with negative mass energy, which is a mind-bending concept in itself. While current science suggests that naturally occurring traversable wormholes are highly unlikely, Thorne doesn't rule out the possibility that we might be able to artificially create them someday.
Okay, that's both terrifying and exhilarating at the same time. But how do you even begin to explain how something like that would even be possible?
He delves into some seriously mind-bending territory with this concept of the bulk. Imagine, if you will, a higher dimensional space where our universe is just one brain existing within it. This is where things get really wild.
Wait, so you're saying there could be other dimensions beyond our own, like beings existing in this bulk that we can't even perceive?
Thorne suggests exactly that. And he proposes that gravity might be the only force that can leak into this bulk, potentially explaining some of the mysteries of our universe.
This is blowing my mind. So this bulk, this higher dimensional space, it could be the key to understanding how wormholes might work, and maybe even other things we can't even imagine.
Precisely. It's like opening a door to a whole new realm of possibilities, a reality beyond our current comprehension. And that's just the beginning of what Thorne untacks in The Science of Interstellar. And this bulk, this idea of other dimensions, it's not just theoretical, you know. Thorne connected it to those gravitational anomalies we see in Interstellar, those strange events that seem to defy the laws of physics as we know them.
You mean like the falling books in Murph's room? Those always freak me out. Are you saying those could be explained by something in this bulk?
That's exactly what he's suggesting. Thorne explains that those anomalies, they're like deviations from how we currently understand gravity. And some of those deviations, well, they're happening in the real world too.
Okay, now I'm really curious. What do you mean?
Think about the strange orbit of Mercury, for example, or the mystery of dark matter. Even the accelerating expansion of the universe. These are all things that our current models can't quite explain.
So you're saying these real-world mysteries and those creepy events in Interstellar, they could have a common thread, something to do with this higher dimensional space. That's wild.
Thorne is a master at connecting those dots, that's for sure. And speaking of connections, let's talk about Professor Brand's famous equation. Remember, his life's work trying to crack the code of gravity.
Oh yeah, the one he was scribbling on those blackboards.
That's the one. Thorne explains that equation as Brand's attempt to mathematically describe the bulk and how it influences our universe. It's like trying to put a higher dimension into mathematical terms. It's pretty mind-blowing stuff.
It's like he was trying to write the rule book for a game we didn't even know we were playing. But if we could understand those rules, imagine the possibilities, right? Could we control gravity like they do in the film?
That's the ultimate question, isn't it? And Thorne doesn't shy away from it. He connects Professor Brand's quest to the very real search for a theory of quantum gravity. You know, that holy grail of physics that would unite quantum mechanics and general relativity.
So Professor Brand's equation, it's like a fictional glimpse into what a real breakthrough in physics could look like.
Absolutely. It shows us the incredible challenge physicists face, trying to reconcile our understanding of gravity with all the weirdness of the quantum world.
Okay, before we go too far down that rabbit hole, let's back up for a second. You mentioned earlier that Thorne goes beyond what we see on screen. What are some other things he explains in the book that weren't in the movie?
Well, for starters, he dives deep into the science behind those incredible visuals of Gargantua, explaining how they were created using real physics equations. He actually worked with the visual effects team to make sure those depictions were as accurate as possible.
Wait, so those images, those weren't just artists going wild with special effects. They were based on actual science.
You bet. Thorne provided the equations, and the visual effects team used those to create those stunning images of the black hole, the accretion disk, the way starlight gets. It's amazing.
That's incredible. It's like art imitating science or science inspiring art. Maybe a bit of both. But back to the physics for a second. Earlier, we were talking about black holes as these points of no return. But what would it actually be like to approach one? Would you even notice crossing the event horizon?
That's the crazy part. According to Thorne, you wouldn't. From your perspective, if you were falling in, you wouldn't feel any sudden jolt or anything. Crossing the event horizon would be surprisingly uneventful,
Yeah.
just a continuous journey into the abyss.
So it's all about perspective, right?
Mm.
What seems like a hard line in space from the outside is just another point in space-time for someone falling in. That messes with my head.
It's all relative, right?
Yeah.
And while we're talking about things that mess with our understanding of reality, Thorne also mentions this concept of naked singularities.
Naked singularities, what are those? Black holes that forgot to get dressed.
Not quite. There are these hypothetical singularities that aren't hidden behind an event horizon.
Wait, so you're saying you could have a singularity just hanging out in space, visible for all to see? Wouldn't that, like, wreak havoc on everything around it?
You'd think so, right? But most physicists, Thorne included, believe that naked singularities are probably forbidden by the laws of physics. It's like the universe has this built-in safety mechanism to keep those points of infinite density safely tucked away.
Whew, that's a relief. Okay, so we've got black holes, wormholes, other dimensions, time dilation. It's a lot to process. Where do we even go from here? What other mind-blowing concepts does Thorne explore?
He touches on one of the most tantalizing questions in science fiction: time travel. And not just in the sense of time dilation, but actual back and forth through time travel, potentially using those wormholes we were talking about earlier.
Time travel through a wormhole. Okay, now you're just messing with me, right?
Yeah.
Isn't that just, pure science fiction?
Thorne acknowledges the immense challenges, not to mention the paradoxes, that come with the idea of time travel. But he doesn't dismiss it entirely. He explores this concept of closed, time-like curves, these theoretical pathways through space-time that could, in theory, allow for journeys back in time.
So you're saying time travel might not be completely impossible, just highly improbable and full of paradoxes. My brain hurts.
That's the effect Thorne has on you, right? He makes you question everything you thought you knew about the universe. But remember, even when he's talking about these really speculative concepts like time travel, he always brings it back to the science, the known laws of physics, and the limits of our current understanding.
It's like he's giving us this guided tour through all the wildest possibilities of the universe, but he never lets us forget our map and compass, making sure we don't get completely lost in the hypothetical. But before we lose ourselves in the possibilities of time travel, I'm curious to circle back to something you mentioned earlier, exotic matter. What exactly is it, and why is it so crucial for these wormholes?
That's a great question. Exotic matter is like the magic ingredient for making wormholes possible. To put it simply, it's matter that has negative mass energy. Now, we've never actually observed this type of matter in the universe, but its existence is theoretically possible according to some interpretations of Einstein's theories.
Okay, negative mass. That sounds like something straight out of Alice in Wonderland. How can something have negative mass? Wouldn't it just float away?
That's the thing about exotic matter. It behaves in ways that are completely counterintuitive to our everyday experience. While normal matter attracts other matter through gravity, exotic matter would actually repel it. It's like having anti-gravity material.
Anti-gravity material. Okay, now we're really in science fiction territory. But I have to ask, if this exotic matter is so, well, exotic, why do scientists even think it could exist?
That's where things get really interesting. Thorne explains that while we haven't directly observed exotic matter, there are certain phenomena in the universe that could be explained by its existence. For example, the accelerating expansion of the universe, which we currently attribute to something called dark energy, could potentially be explained by a form of exotic matter with negative pressure.
So you're saying this exotic matter, this thing we've never even seen, could be the key to understanding some of the biggest mysteries in the universe. That's mind-blowing. But if it's so important, how come we haven't found any yet?
That's the million-dollar question, right?
Yeah.
One possibility is that it's incredibly rare. Maybe it only exists in these extremely small quantities or in very specific places in the universe, like near black holes. Another possibility is that our current methods of detecting and observing matter just aren't sensitive enough to pick it up.
So it's like searching for a needle in a cosmic haystack. It's out there somewhere, but we just need to know where to look and how to see it, right?
Exactly. And that's part of what makes the search for exotic matter so exciting. It's a true frontier of scientific exploration, one that could completely revolutionize our understanding of physics and open up possibilities we can't even imagine.
Possibilities like traversable wormholes. Imagine the things we could do if we could actually travel through these cosmic shortcuts. But I also have to wonder, if this exotic matter does exist and it behaves so differently from normal matter, what are the implications? could it be dangerous?
That's a great question, and one that Thorne definitely doesn't shy away from. He acknowledges that exotic matter, if it does exist, could have unpredictable and potentially dangerous properties. Imagine trying to contain something that literally repels gravity.
That's a scary thought. So while exotic matter holds the key to unlocking some of the most incredible possibilities in the universe, it also comes with its own set of risks and unknowns.
Absolutely. And that's something we need to keep in mind as we continue to push the boundaries of what's scientifically possible. But enough about hypothetical matter and hypothetical dangers. Let's talk about something a little more concrete: the immense power of black holes.
And when you say power, I'm guessing we're not just talking about gravity here.
We're talking about energy on a scale that's almost impossible to fathom. Thorne describes how black holes can literally rip apart stars, creating these swirling disks of superheated gas, what we call accretion disks, and spewing out powerful jets of radiation that we can detect from billions of light years away.
So black holes aren't just cosmic vacuum cleaners, they're more like cosmic engines, powering some of the most energetic events in the universe.
Exactly. And those swirling disks of gas, those accretion disks, they're not just pretty light shows. Thorne explains how all that matter falling into a black hole releases a tremendous amount of energy, which heats up the accretion disk and causes it to glow incredibly brightly.
And that's what we see as quasars, right? Those incredibly bright objects that we can see across billions of light years, powered by these supermassive black holes.
You got it. It's a reminder that even in the darkest corners of the universe, there's this incredible amount of energy and activity, and it's all driven by these enigmatic objects we call black holes.
It really makes you feel quite small, doesn't it? Here we are, going about our daily lives, and out there, black holes are tearing apart stars and shaping the evolution of galaxies.
It definitely puts things into perspective, doesn't it? But it's also awe-inspiring when you think about the sheer forces at play.
It does make you wonder, if black holes are capable of releasing that much energy, could we ever harness it?
Now you're thinking like a true scientist. Thorne actually explores that very question. He talks about some theoretical concepts, like the Penrose process, which suggests a way to extract energy from the rotational energy of a spinning black hole.
The Penrose process sounds intriguing, but also more than a little terrifying, considering where all that energy is coming from.
Indeed. But it reminds us that even the most extreme and dangerous objects in the universe could potentially be harnessed if we can unlock the science behind them.
Okay, but let's not get ahead of ourselves. We're still a long way off from building black hole power plants. For now, I'm content with just trying to wrap my head around the basics of black hole physics, and Thorne certainly gives us plenty to think about.
He certainly does. And one of the things I really appreciate about his book is that he doesn't shy away from the big questions, the philosophical questions that arise when you start thinking about these mind-blowing scientific concepts.
Like what it would mean for humanity if we really could travel through time or harness the energy of a black hole.
Exactly. He challenges us to think not only about what's scientifically possible, but also about the ethical implications of our pursuit of knowledge.
It's a good reminder that science isn't just about cold, hard facts and equations. It's about exploring those big questions, the mysteries of the universe and our place in it all. And the science of Interstellar, it's a fantastic guide for that journey. That whole thing with Professor Brand's equation, it really stuck with me. This idea that he's searching for this formula, this key to unlocking the secrets of gravity. It felt almost mythical.
Oh, absolutely. It was like the driving force of the whole mission, this belief that if he could just crack the code of gravity, humanity could escape a dying Earth. But here's the thing. As Thorne explains in the book, the science behind that equation, it's just as mind-blowing as the fictional scenario itself.
So there's real physics underpinning this seemingly magical equation. Tell me more.
Thorne dives deep, suggesting that Professor Brand's equation is really his attempt to describe the bulk, that higher dimensional space we've been talking about, and how it influences our universe. Imagine trying to define the laws of a higher dimension using math.
Trying to fit an ocean into a teacup is probably easier. But Thorne didn't just pull this equation out of thin air, did he? He actually worked out the math.
He did. Thorne developed actual equations that could govern how a higher dimension might interact with our own, giving a kind of mathematical framework to Professor Brand's quest. Of course, he acknowledges we're nowhere near that level of understanding in real life.
So it's like a fictional glimpse into what a real breakthrough in theoretical physics might look like.
Exactly. It really highlights how much we still don't know about the universe and the forces that govern it. Professor Brand's equation, fictional as it is, it points to this huge unsolved problem in physics, The search for a theory of quantum gravity.
The holy grail of physics, right? A theory that could unify our understanding of gravity and the quantum world. It seems like a long shot, trying to reconcile those two.
It's a challenge that has stumped physicists for decades. But think about it. If we ever did find that missing link, who knows what we could accomplish? Maybe even the kind of control over gravity that Professor Brand was chasing after.
It's tempting to imagine the possibilities, but also a little frightening, right? If we could manipulate something as fundamental as gravity, who's to say we wouldn't mess it up?
That's a question Thorne grapples with. He wants us to consider the ethical ramifications of having that much knowledge. What if we reach a point where we can actually manipulate the very fabric of space-time? Will we be ready for that kind of power?
It's a question that goes way beyond physics and into, well, philosophy, ethics, the whole shebang. It makes you wonder if some knowledge is better left alone, or at least handled really, really carefully. But going back to the film for a moment, there's this one concept I still struggle to wrap my head around, the Tesseract. That scene where Cooper gets thrown into this higher dimensional space. Visually, it was stunning, but what was actually going on?
So Thorne explains that the Tesseract in Interstellar is meant to be a visual representation of five-dimensional space, something that's, well, almost impossible for our three-dimensional brains to even picture.
I can barely imagine 4 dimensions. How do you even begin to explain something like that?
Thorne uses a really clever analogy called a flatland analogy. Imagine you're a two-dimensional being living on a flat plane. All you can perceive is length and width. Height doesn't even exist to you. Now imagine a three-dimensional object like a sphere passing through your plane. All you'd see is a series of circles changing in size.
Okay, I think I see where you're going with this. So we're like those flatlanders, and the Tesseract is like that sphere, right? We can only see these glimpses, these shadows, but not its true form.
Exactly. Thorne suggests that higher dimensions, they could exist all around us, but we just don't have the ability to perceive them directly. And the Tesseract in Interstellar, it's a way to visually represent how we might interact with those dimensions, even if we can't fully understand them.
It's a humbling thought, isn't it? That our reality, it might just be this tiny sliver of a much vaster, multidimensional universe. It makes you wonder, what else is out there, just beyond our grasp?
That's the magic of science, don't you think? It pushes us beyond what we think we know, shows us how much more there is to learn. And honestly, the science of Interstellar, it's a perfect example of that. Thorne takes these really complex ideas and makes you excited about the universe and our place in it.
Couldn't have said it better myself. It reminds us that science isn't just about memorizing facts and formulas. It's about wonder, asking the big questions, and daring to imagine what's possible. So next time you look up at the night sky, remember, the universe is full of mysteries waiting to be uncovered, and some of them, well, they might be even wilder than we can imagine.